Hi, I'm Mike Stanzik and this is Digital Electronics Classroom. In this video we're going to look at sequential circuit design. In the last video we watched sequential circuit analysis, and I recommend that you watch that video before you watch this one. In this video we're going to take a D flip-flop setup. We're going to start with a state diagram and look at the states that we want and how they transition between each other. And we're going to use that to build a state table. And then from that state table, we'll generate state equations, and then finally we'll generate the actual circuit diagram. And so that's our path. Let's get started. Sequential circuit design. All right, so I don't have a story attached to this one, but from a designer point of view, we want to accomplish a task. And then we ask ourselves, what do I need to accomplish this task? So in our imaginary task, we need 2 flip-flops, or we need 4 states to accomplish the task. And the way I draw the diagram doesn't really matter, so I draw it in a way that it makes the most sense. And so in this kind of diagrammic flow, we have sort of an outward flow to an inward upward flow, like an outward downward to an inward upward. And so we have, let me label the state values first. So I'm assuming the center one is going to be 0, and I'm going to do 0, 1, 1, 0, 1, 1, just like this, okay? And so you could label them however you like. So I'm going to kind of have these 2 arrows going outward and downward like this. And we'll say that a 0 will go to the left path and a 1 will go to the right path, and they both output a 1 when that happens. Okay, and let's feed this 0, 0 upward here. And when that happens, that happens on a 1, but it's kind of just resetting itself, so it's not going to actually output anything. And then if it has in this state and it gets a 0, we're just going to come back. And so this is 0, 0. So that there's no output when you're in the 0, 0 state. Now these guys will both feed into the 0, 0 state. So this is sort of that out and back up the middle. And that will occur on a 1 for each of these. And then when that does happen, they will output. And if it doesn't get a 1, we're going to have them switch states. And so they'll jump back and forth to each other like this. And that occurs on a 0, and then it's a 0, 0. So that's that is our state diagram. And if you kind of squint your eyes, it sort of looks like a one-eyed duck looking straight at you. Yes, the beauty of digital electronics. Okay, so we have the present state, and that's A, B, and then our input X. And now we're going to have our next state. That's going to be A and B, and then our output Y. And so then we look at the state diagram to generate our state table. And so let's see, if I'm at 0, 0, and there's a 0 comes in, I stay at 0, 0, so I stay at 0, 0, and there's a 0 output. And if I'm at 0, 0, and a 1 comes in, then I go to 0, 1, and there's a 0 output. If I'm at 0, 1, and a 0 comes in, I go to 1, 0, and there's a 1 output. If I'm at 0, 1, and a 1 comes in, I go to 1, 1, and there's a 1 output. If I'm at 1, 0, and a 0 comes in, I go to 1, 1, and there's a 0 output. If I'm at 1, 0, and a 1 comes in, I go to 0, 0, and there's a 1 output. And if I'm at 1, 1, and a 0 comes in, I go to 1, 0, and there's a 0 output. And then if I'm at 1, 1, and I go to, and a 1 comes in, I go to 0, 0, and there's a 1 output. So we've generated these 3 columns, one for the next state for A, one for the next state of B, and then one for the output Y. And so now I want to generate my state equations. And the state equations come about from doing a simplification of each of these columns. And so we're going to use K-maps to do that. So here this will be for A, next A, this will be for next B, and then this will be for the output Y. And then my inputs are present A, B, X, and then present A, B, X for each of them. Present A, B, X. And so let's fill this truth table in, or this kernel map in, I'm sorry. So we got 0, 0, skip, 1, 1, and then 1, 0, skip, 1, 0. And so highlighting these boxes right here, I can see that that's what my kernel map simplification is going to look like. So I got A of t plus 1. Next A is going to be A naught and B, or A and X naught. So there is my A state equation. Okay, so let's do B. 0, 1, 0, 1, 0, 1, skip, 0, 1, and 1, 0, 0, 0, 1, 0, 0, 0. Doesn't matter if we skip because they're both zeros. So let's go ahead and write out B. So B of t plus 1 is equal to, well, we have this boxing of 2, and unfortunately we have a singleton right there. So we have A naught and X, or, and then this is A, B naught, X naught. There we go. And then for Y, we have 0, 0, 1, 1, 0, 0, skip, 1, 1, and then 0, 1, 0, 1, 0, 1, skip, 0, 1. So here is pretty clear. We got these two boxes like so. And so we have, excuse me, sorry, we have Y is equal to, the top one here is A naught B. And then the bottom one here is A and X. Okay. One thing we will notice here, and you don't have to do this, that's not the goal right now for us, but we'll notice that there is a term A naught B that's in both Y and A. And so if I use an AND gate to build that term in my circuit diagram, it doesn't make sense to use another gate to build that term again. And so typically we'd want to pull from the output of that AND gate and then directly into the OR for the Y, or vice versa, when we actually make that circuit diagram. So we'll see, maybe we'll do that. Okay, I just want to label these here. So this is the state diagram. This is the state table. And then these are the state equations. Okay, and then lastly we're going to build the circuit diagram, or the gate network, or there's lots of the schematic, lots of ways that people describe these things. Okay, all right, so let's go ahead and do that final step. So I need the equations to do that. That's the easiest approach. So let's set up. We got 2 flip-flops that we need. And we're using D flip-flops to make life a lot easier. And we have our D and our clock, and we have our A, and we have our A bar. And so instead of writing Q and Q bar here, I'm writing A and A bar to designate that as the A flip-flop. And then we have D, our clock. We have B and B bar. And then each of these will have a bubble on the output designating them as inverted outputs. Okay, and so we have A, we have B, and then we'll have a Y output over here. Okay, so let's build the first one. We got and feeding into an OR. So 2 input and into an OR, and that goes into the D input of A. So we have our OR, and then I'm going to have a 2 input and a 2 input and they're going to feed into that OR. Alright, so what goes into the first AND gate? It's A bar and B. And so I need A bar. Ooh, maybe I'll do this. We'll use some colors here. So, do I want to? Okay, let's do it. A bar and then here's B. I'm just going to take B up through the middle here. Perfect. And then we got A. And X bar. So I have to build X. And X bar. So here is X. And here is X bar. So we need X bar. Okay, well, I guess that one's going to be black. And so that's that first setup. So the next one, we need A bar X or A B bar X. So again, I need an OR gate that has 2 inputs with an AND gate that has 2 inputs, and then an AND gate that has 3 inputs, like so. Okay, that goes into B. And the D input, and saying that the next state will be whatever that comes out of that OR gate. Okay, and so now we have A bar X. So here's A bar. A bar is also up here. I'm going to take it from here. A bar, and then here is X. Alright, and then we have A, B bar, X bar. So where is A? A is right here. I'm going to take it from here. A, and then I need B bar, which we haven't gotten yet, so I'm going to take it around. B bar, and X bar, which is right here. Okay, great. And then lastly we have A bar B or A X. Okay, so that's for Y. So end with an OR. And then we have, let's see, where is A bar B? So that's that first term right here. So this is A bar B. So we can take from here and go straight down with this. And now that's A bar B. A bar B right there, and AX. A is right here, so pull A. We need an AND gate for this. A and X. X is right here, so we'll pull X. And there it is. Look at that, it's beautiful and colorful. So this circuit diagram implements these state equations, and these state equations came from this state table, which was generated by interpreting this state diagram, which was what our designers wanted. And so this is what we call the sequential circuit design, starting with a brainstorm of what do you want to happen, building a state diagram that represents that, and then letting it roll from that point, generating a state table, state equations, and eventually a circuit diagram that you can implement. Thanks as always for being with us today. I appreciate all your viewership, and hopefully you're finding these videos to have value for you. My name is Mike Stanzik. This is Digital Electronics Classroom, and as always, have a wonderful day.